Good afternoon everyone. Today we will start the new topics of interference as a Newton's ring. The interference due to the Newton's ring by reflected light, transmitted light. There are three scientists developed the interference phenomena by using a thin film. The first scientist is a Newton's ring, second one is a Hooke, and the third one is a Young's one. The Newtons consider the plano-convex lens and the plane glass plate and form the thin film between the plano-convex lens and the plane glass plate. The second scientist, Hooke's one, he considered the thin film of a mica sheet and observed the different colors. And the third one, the Young's one, Young's scientist developed the interference phenomena of thin film, the reflection from the upper portion of the film as well as the lower portion of the film. But today we will observe or study in detail the Newton's ring. First, how to develop or formation of a Newton's ring and the experimental arrangement of a Newton's ring. Now, for experimental arrangement, the Newtons consider the plano-convex lens, place on a one plane glass plate. Here we consider the plane glass plate. The rays are incident normally. Here we consider the lens and all three from the monochromatic source of a light. They are incident here. This is microscope, glass plate. This one is plano-convex lens. This is plane glass plate. There is a formation of a air thin film. This source is a monochromatic source. Now the experimental arrangement of a Newton's ring, it consists of the source as a monochromatic source as a sodium vapor lamp, then the lens, converging lens, the third one is a glass plate, microscope, plano-convex lens and a plane glass plate. Now here when the monochromatic source is on, that source in the form of a scattered beam which can be converted into the converging lens or the parallel beam, that can be converted by using a converging lens L, and this converted parallel beam is incident exactly at 45 degree to the plane glass plate or inclined at the plane glass plate. Here partial reflection and refraction take place. Reflected rays are incident exactly normal to this plano-convex lens, and here these rays again internally refracted in a plano-convex lens. Again here reflection take place, again multiple reflection in a film is take place, and again refraction, and the rays are emerged out. Now here these rays are incident normally to the plano-convex lens, and these are the emerge out from this whole system of a Newton's ring. They are also reflected in upward direction, these are in downward direction. So both the rays are in superposition to each other, and when the two waves or two rays are superposition to each other, there is a formation of a Newton's interference pattern. Now here those interference pattern is obtained, that interference pattern around the point of contact between the plano-convex lens as well as a plane glass plate, because there is a formation of a thin film from the point of contact. The air film goes on increasing from point of contact to the left hand side as well as the right hand side. The thickness is increases from the point of contact. At the point of contact, the thickness is nothing but a 0, 1. Now here this whole system again we are consider as a plane and transparent. So the rays are reflected in upward direction and these rays are in a downward direction. both rays are superposition to each other, there is a formation of a interference pattern, and that interference pattern around the point of contact in the form of a concentric rings. So, this pattern first observed the Newton's, and he gave that interference pattern his own name as a Newton's ring. Now, how the formation of a Newton's ring we are consider? Here we will consider the plano-convex lens, which is placed on a plain glass plate. When the rays are incident normally to that one, there is a reflection take place in case of plano-convex lens. Again at here there is a refraction take place. Again here the reflection, multiple reflection in a film, and the rays are emerge out. Suppose these are R1, A, B, C, D, E and R and R1. So, here AB as a normal incident ray, BC is a partial refraction in a denser media as a plano-convex lens, and the BR is a reflected rays. At point C, there is a refraction take place in a thin film along the direction CD. At point D, the multiple reflection in a thin film take place, and at point E again there is a change from air media to the denser media, and denser media to the again air media, or we can say that we are obtain two waves from the single source of a incident ray. So, here BR and FR1 are the two parallel beam we will get from the single source of a monochromatic cell, and whenever these two parallel beams are there, then we can calculate the path difference between these two parallel beam, as well as we already find in a thin film delta is equal to 2 mu t cos of r plus or minus lambda by 2. This is the path difference between the two reflected rays in a thin film. Now, here for formation of a Newton's ring, also there is a formation of a two sources, two light waves or two beams from a single incident beam, and these two beams are superposition to each other, then there is a formation of a Newton's ring around the point of contact. And here we observe the number of rings around the point of contact. The center spot is a dark one, because the thickness of that one is a nothing but the 0. If we substitute here the value of t is equal to 0, then the path difference here also the 0. That is why the center spot we can observe as a dark spot. And here number of rings we are observing of equal thickness around this point of contact. The each ring is due to the locus of a point in that particular thickness of a thin film. Around that point of contact at the specific distance, the thickness is a constant for all the points around the point of contact. Suppose this we will consider the R1 is the first ring, radius of a first ring is R1. For R1 is a locus of a point around that point of contact, the thickness and around that one is nothing but T1 is nothing but the same for each one. If suppose second ring we are consider, the second ring also R2 is the radius of a second ring, Newton's second ring, then which having a thickness as suppose T dash. This T dash thickness is around that whole, around the point of contact at distance R2 is nothing but the same. So, the number of concentric rings we can observe of equal thickness and equal spacing from the each other. Then the conditions for Newton's ring due to the reflected light, actually this one keep as it is. Now, here we will calculate the path difference and the radius of a Newton's ring. Here we consider L, O, L dash and which is placed on a glass plate. This is the center C, which is here, that is the radius, and this one is nothing but thickness of the film, and here Rn is the radius of a Newton's ring. Here we will label as P, here N, Q, now by using the Newton's ring, due to the reflected light, those pattern we are observed, that pattern having the center spot as a dark one and around that the number of concentric rings. This is the Newton's ring due to the reflected light. Now we already see that formation of a Newton's ring, plano-convex lens placed on a plain glass plate, the one ray incident beam converted into the two parallel beam, and then we will get the interference pattern because these two wavefronts are parallel to each other, and when these two are superposition to each other, there is a formation of a interference pattern, and that patterns is the concentric rings. Now the same thing we are consider, or same plano-convex, and we will convert into the circular path, which taking the radius of curvature, suppose R is the radius of curvature of a plano-convex lens. For calculating the value of thickness of this film, we will convert this plano-convex lens in the form of a whole circle with the radius as a Rn. Suppose small Rn is the radius of a Newton's ring from the center point to the thickness at the T1. And now our aim to find out the conditions for maxima and the minima for a particular rings. That conditions are nothing but we already defined inner interference due to the thin film, the conditions for the bright as well as condition for the dark fringe. First of all, we will consider for the bright fringes 2 mu t cos of r plus or minus lambda by 2 is equal to n lambda. So here 2 mu t cos of r equal to 2n plus or minus 1 lambda by 2. But here the rays are nothing but incident normally to the plano-convex lens. So the value of this cos r is nothing but 1, because whenever the normally incident, the reflected angle of refraction is 0, cos 0 is nothing but 1, and here the film is nothing but air film. So the value of mu is a 1. Same equation we can substitute the value of cos r, and the mu is equal to 1, cos r is equal to 1. Then the same equation we can write as 2t is equal to 2n plus or minus 1 lambda by 2. Similarly, we can find the condition for a bright fringes. This is for bright. Then we can calculate for the dark fringes. Now for dark fringes, the condition is 2 mu t cos of r plus or minus lambda by 2 is equal to the odd multiple of lambda by 2. Now we will get 2 mu t cos of r is equal to n lambda. Again here cos r and mu values are nothing but 1. So we will get 2t is equal to n lambda, and suppose denote the equation number 3. Now our aim to calculate the value of a thickness as a t. Now for calculating the value of t, here we consider LOL dash is the plano-convex lens, which is placed on a glass plate. Suppose G dash is a glass plate. The point of contact for plano-convex lens and the glass plate is nothing but at O. Now here the radius of curvature of a plano-convex is considered as a R, and here we will label as LOL dash. Okay. Now we will consider here one of the right angle triangle that can be formed as a CNP. At N there is a right angle triangle. According to the law of Pythagoras, we know that hypotenuse square is equal to the height square plus base square. Now what is the hypotenuse here? Hypotenuse is equal to here hypotenuse is nothing but Cp square is equal to base square as Np square minus Cn square. Now what is the value of Cp? Cp is the radius of plano-convex lens, that is R square is equal to Np square. Np square is nothing but radius of a nth ring as Rn square plus now Cn. That value we have to calculate here. Now this total distance is nothing but the R, that is the radius of a plano-convex from center to the any part of a point on a circular scale. That is the total distance is R. This distance is nothing but the T, but our aim to calculate this distance Np, that Np is nothing but total R minus of the small t, that is R minus T. We will get the distance as a Cn. So Cn value we will substitute R minus of T bracket square. Now solve this one. Rn square plus R square minus 2RT plus T square is equal to the R square. So R square is equal to Rn square minus 2RT plus T square, and here Rn square. R square get cancelled from the both the side. R square and this R square get cancelled from the both the side. So this value is 0. So we will get Rn square is equal to T square minus 2RT. Now here T is the very small. If we are consider the T square, that T square value is again the very small. If the thickness is very small, then square is also the very small. So we can neglect the value of a T square. So we will get Rn square is equal to 2RT. So the value of T is nothing but Rn square upon 2R. That is the thickness of a thin film produced between the plano-convex lens and the plane glass plate. Now this value of a T we can substitute in equation 1 as well as equation number 3. Suppose we will substitute in equation 1, we will get 2T is equal to 2n plus or minus 1 lambda by 2. So we will get 2 into Rn square upon 2R is equal to 2n plus or minus 1 lambda by 2. 2 get cancelled, we will get Rn square is equal to 2n plus or minus 1 lambda r upon 2. Now here this radius we will convert into the diameter. We will get diameter as a dn. Rn dn is equal to 2 times n. So the Rn's value in terms of diameter, it becomes dn square upon 4 is equal to 2n plus or minus 1 lambda by 2 times r. Now we will get d square is equal to 4 2n plus or minus 1 lambda r upon this 2. 2 divided by 4 we will get here 2. Now here this whole factor lambda is constant, r is a constant, only the variation factor is nothing but n is starting from 0, 1, 2, 3, 4. So, we can consider dn is equal to the square root of 2n plus or minus 1 lambda by lambda r. Now, from that one we can say that the diameter of a nth ring is directly proportional to the square root of a odd natural integer number, that is the dn is directly proportional to the square root of a odd natural number, and denote equation number 5. Now, the same value of a t we can substitute for our dark fringes. Now, for dark fringes we observe that the 2 into t value is a rn square upon 2r is equal to n lambda. So, rn square is equal to nr lambda, and in terms of diameter we will get d square n is equal to 4 nr lambda. So, the value of dn is equal to square root of 4 nr lambda, and the value, then we can say that dn is directly proportional to the square root of a natural number, and then the equation number 5. This equation 4 and 5 we can say that the diameter of a nth dark ring or a bright ring is for the dark ring which is directly proportional to the square root of a integer number as a n, and if the bright fringes are there, the diameter of a bright fringes is directly proportional to the square root of a odd natural number. These are the diameter of a nth and the diameter of a dark and a bright nth ring. Now, the Newton's ring due to the transmitted light is exact reverse case we will observe. Conditions are the reverse one, but all things are nothing but equal. So, the Newton's ring in transmitted light, here same thing we will consider. Plano-convex lens placed on a plain glass plate. Here the light rays are incident on that one, then there is a reflection take place, refraction take place, multiple internal reflection take place, and the rays are emerged out at the bottom. Suppose these are the T and the T1, this one is A, B, C, D and E. Now, in a transmitted light, here we consider AB as a monochromatic source which is incident on that plano-convex lens, partial refraction take place along the direction BC. At point C, the refraction in a thin film is take place. At point D, the rays are emerged out along the direction DT. And at point D, this is the partial refraction and the partial reflection along the DE. And at point E, again the internal reflection take place and the rays are emerged out along the direction ET1. So, DE and ET1 are the two transmitted rays, and these two transmitted rays are again superposition to each other, and we will get the interference pattern around the point of contact. But here those type of patterns we are observed in a transmitted light, the center spot is nothing but a bright one. In transmitted light we will get the center spot as a bright one, and in case of reflected light we will get the center spot as a dark one. Now, the exactly similar way we will find out the conditions for the bright fringe as well as a dark fringes. Now for bright fringe, the delta is 2 mu t cos of r is equal to n lambda. So we will get 2 mu and the cos r is again the 1 for that one. So 2t is equal to n lambda. The value of t we can substitute, or afterwards this is the condition for the bright fringe. Now similarly we can find the for dark fringes. Dark fringes 2 mu t cos of r is equal to 2n plus or minus 1 lambda by 2. Again mu is 1 for air, cos r is again 1. So 2t is equal to 2n plus or minus 1 lambda by 2, and denote equation number 2. We already calculate the value of t as a thickness in the plano-convex lens and the plano-convex lens and plain glass plate. That one is nothing but 2 Rn square upon 2r. Now we will substitute this t value in equation 1 and equation number 2. So in equation 1 we will get for bright fringes we will get 2 into Rn square upon 2r is equal to n lambda. So Rn square is equal to nr lambda, and d square n is equal to 4 nr lambda, and then d is equal to square root of 4 nr. So dn is directly proportional to the n. Now here this diameter of a dark bright fringe, in case of a transmitted light, dn is directly proportional to the square root of a natural number. This condition is exactly inverse of due to the Newton's ring due to the reflected light. There is a odd multiple of the integer number. Now for dark fringes, we will substitute the same thing in the equation number 2. 2 into r square upon 2r is equal to 2n plus or minus 1 lambda by 2. So we get Rn square is equal to 2n plus or minus 1 r lambda by 2. So d square n is equal to 2n plus or minus 1 2